Because we need star spectrum. Test the stars.
Por eso creo que
Ha
sido parecido, ¿no?
She helped us a lot. She gave me a lot of pointers.
Okay, cool. Nice.
It was really good.
Okay, now we are live
I
on
was just
YouTube.
discussing them with Lisa this one.
El espíritu era muy...
Okay. Okay. Okay, I think we can start. Okay, this week we have a speaker, Evgenia Koutsoumpou. Did I say Koutsoumpou? She's visiting us with the Erasmus Plus program, and she's doing her PhD at the Kapodistrian National and Kapodistrian University of Athens. She will be here for 2 months till the end of November. She has been collaborating with me in a paper about the effect of cosmic rays on the gas in the AGN and star-forming regions and star-forming galaxies. And this is the topic of the talk today. So, whenever you can.
Hello everyone, Evgenia. As Juan said, I'm a PhD student at the University of Athens. We worked on this project with Juan and the rest of my collaborators, my supervisor in Athens, Professor Pasira, and Dr. Luis Espinosa. And what we did with Juan is we wanted to investigate the impact of cosmic rays on ionized stars within AGN and star-forming galaxies. I will start a little bit more general as an introduction. I'll talk about galaxy evolution, and I'll walk you through the cosmic rays. As you can see here, this is the specific star formation rate over the stellar mass of a galaxy. And you can see here in this galactic sample survey, that these galaxies move. First, they grow. The accretion of mass grows the black hole, and subsequently they move towards dying out. Towards this part is more star forming, and then they begin to have jets and outflows, and star forming is quenched. There is a critical mass over which the galaxies end up to the red sequence. So there are evidence that contribute to the fact that the supermassive black hole in the center of a galaxy, of its host galaxy, plays interplay. There is a complex role between the supermassive black hole and the star formation in its host galaxy. We can see here the dispersion of velocity dispersion of the stellar velocity dispersion over the black hole, and there is the mass of the black hole, and there is a correlation, as we can see. Here as well, we can see the populations I showed you before. In orange, there are the more radio jetted cases, and we can see that the bigger the black hole, the bigger the stellar component of the galaxy at hand. So there must be something there, and of course, the bigger the black hole, the bigger the AGN feedback, the jets, the activity, and in general, the interplay between the gas in its host galaxy. So, going on, I'm going to talk to you about a little bit the different mechanisms that are found in an AGN. For example, there's photoionization from the accretion disk and UV photons that can excite and deposit energy within the clouds. Also, there are the outflows within a galaxy. And moreover, there are shocks, jets and outflows can propagate throughout the galactic gas and heat compress, drive through to the different stages of the gas. As there's also collisions and heating, the different particles can collide with the gas and heat again and excite the gas phases. X-ray heating, of course, because there's an X-ray component to the AGN, which can through photoelectric absorption or Compton scattering give also deposit energy to the gas. And finally, there's cosmic rays, to which I'm going to elaborate more. These are very highly energetic particles coming from the jets or from supernova remnants inside the galaxy. And this is where I'm going to focus. And to begin with, a little bit more generic and come to where we use cosmic rays. You can see here, this is, for example, an environment where cosmic rays can be produced, AGN, supernova remnants, GRBs. And this is the flux of the cosmic rays we receive at the Earth. And when all these particles exhibit different indexes in the cosmic ray energy flux, VS energy plot. And you can see here that there are different populations, There are different populations of cosmic rays, and the different index indicates the different populations of the cosmic rays. In this part, the lower energetic ones are coming from the host galaxy, in our case, the Milky Way. So this part is also alternated by the solar component in the sun drives most of them out. So this part is dominated by the solar cycle. And this part above the angle, as they call it, which are very, very highly energetic particles, is coming from an extragalactic sources. And these so very highly energetic particles are not capable of being constrained by the magnetic field of our galaxy. So this is our reason for saying that they are coming from a source outside the galaxy. So this part, the up to 10 GeV part, is the part that could possibly ionize and interact with gas within the host galaxy. As I said before, this is the spectrum of the cosmic rays inside the Milky Way. So we're not taking this into account, but for our study, because we're studying other galaxies. But this energy range is the range of cosmic rays we need in our study. So how do they accelerate? If we have a jet, this is a black hole, the accretion disk is in this plane, and this is a plasma jet. We have acceleration of cosmic rays within the jet, and the low energy cosmic rays within the host galaxy, which I showed you before are in the lower part for our galaxy and any galaxy as well, are capable of interacting with the gas clouds within the galaxy. The very high energetic cosmic rays are the ones that escape and can eventually reach or may eventually reach Earth. But of course, there is cosmic ray acceleration inside star-forming starburst galaxies as well. We can see here acceleration for supernova remnants. When the gas compresses and can accelerate via shock around the supernova remnant particles, so we can get the cosmic ray component from supernova remnants in starburst galaxies. And then again, there are a lot of MHD simulations as of recent. We can see here the 4 rows. This is from PESCIN 2023. They did some simulations without cosmic rays. The first 2 rows are without cosmic rays, and the last 2 rows are with cosmic rays. And what you can see here is the X, Y plane on the first and the third row, and the Y, Z plane on the second and the fourth row. And you can see here in the Y-X plane that they start their simulation within flowing material. And as the time evolves, this becomes an accretion. And on the YZ plane, you can see the outflowing material. And in the color bar, there is the temperature of this outflowing material. And you can see that this temperature is high enough. It's orange, so 10 to the 6th Kelvin, something like that. In the case of when they added cosmic rays into their simulations, again, we have the same, almost the same picture in the YX plane, in flowing material and the accretion disk. But when we go to the XZ plane, we can see here that the outflows are more, and in particular, there are more colder outflows. Here you can see that there are outflows with in the color purple, orange, something like that, which is a lower temperature gas than those without the cosmic rays. So what they said, and other scientists in this particular field said, is that we can see here that with the non-cosmic rays, the outflows are very high in a very high temperature, whereas with the cosmic ray component, we have outflowing material from the colder gas phase. This indicates that when you strip a galaxy from its colder gas component, it's probably you probably cleanse the star formation in the galactic disk. So a few facts. As of now, cosmic rays have been studied in molecular gas and their impact on molecular gas. In general, on the ionized and atomic gas, they heat and produce secondary ionization. There are also studies that say that, like Fernand 2009, that above 10 to the minus 13 cosmic ray ionization rate, they mostly contribute to the heating and not the dissociation of molecular hydrogen. And this old study says that they can also influence nebular emission light, which is our main focus next. What I'm showing on the right column is the study, the theoretical model of the cosmic ray ionization rate from Padovan 2019, where you can see that they modeled the different with different cross sections for the molecular and atomic hydrogen. They tried to fit the observations within the Milky Way. So these are observational points from gas clouds within the Milky Way. And they tried to fit these with non-thermal emission, with fitting the spectrum, not thermal emission, sorry, with fitting the spectrum of the cosmic rays, assuming at the low energies of cosmic rays I showed you before, a spectrum, and fitting it and finding the cosmic ray ionization rate. Similarly, FAN 2024 did this on NGC-253, which is a starburst galaxy. I'm going to show more next. They did the non-thermal emission in the red dotted dust lines, and they also found the cosmic ray. They added the cosmic ray ionization rates from different molecular chemistry studies. These are H22 and B22 are cosmic ray ionization rates estimations from different works where they studied the molecules within this galaxy. So you can see here also the range of the cosmic ray ionization rate. It can be as low as 10 to the 15 or 10 to the 17 in the galaxy, in our galaxy, but it can go a bit higher. Okay, this is. So what we did next, we wanted, as I said, to study the ionized gas. And to do that, we employed the PPD diagrams. The PPD diagrams are diagnostic diagrams which utilize the emission line ratios at hand here. You can see oxygen 3 over H beta, nitrogen 2 over H alpha, same y-axis, sulfur 2 over H alpha, oxygen 1 over H alpha. These diagnostic plots are good, as you may know, most of you know, for discriminating the different sources. This is the Curie line, the dark line is the Curie line of cases. And above this, we have the AGN-like sources. And under it, we have the star-forming objects. So this is a way to discriminate, to differentiate the different source if it's an AGN or a star-forming region. Also, you can tell the difference between Seyfert and linear area if they fall in these particular areas. And there are a lot of works that have done this, what we're going to do as well. They try to model these particular areas on the PPT, which are the aging like Seyfert linear objects. So what was the main motivation behind this work was that works so far have employed mainly shocks and photoionization and not the cosmic rays, even in environments where cosmic rays are expected to be found. And some works used higher tensorial metallicities. For example, Groves 2004 reproduced this particular part of the PPT of this is nitrogen over its alpha, the first PPT. Reproduced this part with models that reach up to 10 to 4 solar metallicities. What we did instead, we incorporated cosmic rays into our models, and we saw their impact deep within the cloud, all that by assuming a solar metallicity. We needed observations, of course, and we employed these for actually 3 galaxies. We used observations from MUSE data of all of them, and this is Centaurus A. We use that because it has very known radio jets and very so there is not evidence. We expect that there are a lot of cosmic rays there. Also, we used NGC 1068, which is also an AGN with more compact jets and also some star-forming regions. NGC 253, which I mentioned before, which has very recent molecular chemistry indications of cosmic ray ionization rate that high. And as a tech source, we used the central area of NGC 1320 because this is a very highly photoionized galaxy, and we wanted to see where the photoionization case lies in the PPT diagrams. So, to our methods, we use the circular apertures to extract the spectra. We selected areas where we could have the PPT lines very clearly, and we used both apertures from the jet rail and outside of it. These are the 3 galaxies I found, and you can see the different apertures we selected. For example, this aperture 2 from Centaurus A, we fitted for all the apertures the PPT lines. We extracted the flux lines and we treated them for extinction with Falsetti's law. And subsequently, we are going to our modeling part. We used Cloudy to have, which is very known, photoionization radiative transfer code. It's very good for our work because it can incorporate cosmic ray ionization rate. And we use 2 different kinds of models in Cloudy, both AGN and star forming. You can see here the spectrum of the AGN case for Centaurus A and NGC 1068, and the spectrum of we used for juxtaposing it with NGC 253 observations. This is a black body spectrum, a simple black body spectrum. And we also had to put a grid, create a grid with parameters for our models. So we used ionization parameters, photoionization parameters from 10 to the minus 3.5 up to 10 to the minus 1.5. A great range of initial hydrogen densities to cover all potential gas phases. And we constrained the metallicity to 1 solar and also got some values for the ionization parameter from the chemistry routines of Perez Montero 2014-2019. You can see here that at most Centaurus A from these routines has 1.2 solar metallicity. So 1 solar metallicity is quite well for our modeling process. And we used the discrete cosmic ray ionization rates from 10 to the minus 14 up to 10 to the minus 12. So, putting all this together to create our own PPTs, what you can see here is the PPTs for nitrogen and sulfur. You can see in red color the different notation for the models based on the ionization parameter logU, as I said before. So from white is up to deep red, you can see the ionization parameter going to higher values, deep red being the highest. And also we have in purple, the crosses are the observational points, in this case of Centaurus A. And in purple, the deeper purple colors represent the areas near the nucleus of Centaurus A, whereas the lighter ones are from areas in further away distances. We also see NGC 1320, the Czech source here in the diamond, the red diamond. And what we see is that the first row is for 10 to the minus 14, and we see that this is not capable of reproducing the observational points of this object. Going a little bit higher to 10 to the minus 13, the models move a little bit to the Seyfert linear area. In the case of nitrogen 2, less. In the case of sulfur 2, they fully cover the Seyfert linear part of the PPT. We went a little bit even higher to 10 to the minus 12. And at this time, we saw that also the observations from nitrogen 2 were covered by our models here in this particular area. In the last row, you can see the same models for 10 to the minus 12 cosmic ray ionization rate, but now they are notated with the densities of the initial densities of the hydrogen. You can see from white is pale green, being the lower densities, and the deep green being the higher densities in our modeling. So we wanted to check that also on NGC 1068 to see if the observations are again covered in that way. And what we see is a very similar behavior. We see that for 10 to the minus 14, these are the very same, the nucleus, the near nucleus observations of NGC 1068, which fall in the AGN-like Seyfert linear area. And we see again that 10 to the minus 14 cosmic ionization rate is not boosting the emission lines in this particular area, nor for nitrogen 2, neither for sulfur 2. But the 10 to the minus 13 again comes close for the sulfur 2 emission. And then again, a little bit higher, the 10 to the minus 12 comes pretty close to the observations of NGC 1068 in the nitrogen case. So this is something we see again in NGC 1068. And then we wanted to check the scenario in with the star forming models with a simple black body, as I said before, to see if a simpler spectrum can have, combined with cosmic rays, has the same behavior. And NGC 253, as I said before, has recent cosmic ray ionization rate measurements from the chemistry, the molecules. So we can see here that the models for the 10 to the minus 14, the lower cosmic ray ionization rate, do not fully cover the observations of NGC 253 in either case, again, nitrogen nor sulfur, but going a little bit higher to 10 to the minus 13, we can see that sulfur 2 again is pretty well covered in the parameter space of the PPT. Okay. Using the greater cosmic ray ionization rate, again, the model jumped to the AGN-like Seyfert area. So our observations for NGC 253 are covered with this ionization rate. Okay, so we wanted to see now what exactly happens to the nitrogen and sulfur 2 emission, and what happens within the gas, the depth of the cloud, to see why is this behavior we see, why do we see the model jump to that area. we constructed plots that study, for example, first the temperature within the depth of the cloud, and we see here, we see here in green the ionization parameter minus 2.6, a higher ionization parameter, lower, sorry, ionization parameter, and minus 2.0, a higher ionization parameter. The behavior between the two, the green and the blue, is pretty much the same. And what changes is the cosmic ray ionization rates. We have the different cosmic ray ionization rates I described before. So we have 10 to the minus 14, the solid line, 10 to the minus 13, the dust solid line, and the dotted line is 10 to the minus 12. Okay. What we can see here is the photoionization dominated part of the cloud. And you can see here that ionization reaches deep within photoionization reaches this part within the cloud after 10 to the 18th centimeter. And what we can see is that the higher ionization rate, 10 to the minus 12, can sustain the gas to a high enough temperature, whereas the lower cosmic ray ionization rates don't have that effect in the temperature. So we wanted to see if this exact behavior happens again in the Seyfert lines. And yeah, we expect here this to be the contribution of the cosmic rays. Okay, this is Seyfert 2. In Seyfert 2, we see here the emissivity within the cloud. And again, for the two photon-dominated areas, we see that the emissivity is boosted in the high cosmic ray ionization rate scenario. For 10 to the minus 12, the Seyfert 2 emission is that high, whereas for 10 to the minus 15, 10 to the minus 14, it drops. It's the same case for both star-forming and AGN models. Again, on nitrogen 2, even though nitrogen 2 is not that much affected as Seyfert 2, but again, the emissivity of nitrogen 2 is boosted in the cosmic ray, in the high cosmic ray scenario, both in star-forming and AGN models. And kind of the same for oxygen 1. Going on H alpha, H alpha first, we see a different behavior. We see that H alpha emission after this particular depth of the cloud is not that much affected as previously showed in sulfur and nitrogen lines. And going on to H beta, we see that H beta is even less affected by the high cosmic ray ionization rate. Oxygen 3 is kind of in the middle, is not that's not affected as the low ionization lines nitrogen and sulfur 2, but it's kind of affected as well. So putting all of these together, we have here all our observational points coming from Centaurus A, NGC 1068, NGC 253, and the red diamond from NGC 1320. We can see the different observational points, and the contours are representing the AGN models for 10 to the minus 12 with purple, and with crimson on the background is the star-forming models for 10 to the minus 12 again, in the case of nitrogen 2. The gray-scaled area is AGN models with a cosmic ray ionization rate near the value of the Milky Way. So this is the value we expect in the Milky Way. And we see here where these models are falling. To the Seyfert 2 PPT diagram, we did the same thing with 10 to the minus 13 cosmic ray ionization rate. And we see again the grayscale, the Milky Way models where they fall. And we see that in neither case, the Milky Way values of cosmic rays can reproduce all of the observations. So it seems like nitrogen 2 needs a higher cosmic ray ionization rate, whereas sulfur 2 needs 10 to the minus 13. And none of these observations can be represented with the Milky Way values of the cosmic rays. So we went on to study what happens within with the temperature and the photoionization. And what we did is we constructed these plots. These plots are showing the ionization parameter from minus 10 up to 6. And Xi is also a different way to express the ionization parameter. And going from the highest ionization parameter towards the lower, we see that in both AGN and star forming models, the three cases, 10 to the minus 12, 10 to the minus 13, 10 to the minus 14, kind of follow the same curves. But going down to a lower photoionization parameter, which is to be expected deep within the clouds where photons cannot reach, we see here that if we do not have a high enough cosmic ray ionization rate, such as 10 to the minus 12, the temperature drops. And this happens for both cases. The temperature drops for the lowest cosmic ray ionization rates, but it kind of is sustained for 10 to the minus 12 to 10,000 Kelvin, which is good enough for ionizing and heating a gas in deeper layers of the cloud. So it seems like high cosmic ray rates can sustain this high temperature within the clouds. Going on to my conclusion, what we propose is that cosmic rays above 10 to the minus 13, especially in environments when we can expect this kind of cosmic rays, should be included as an excitation mechanism in both AGN and starburst. Cosmic rays seem to penetrate deep within the clouds, produce secondary UV photons and UV and ionization, secondary ionization. Their effect is mainly on the low ionization lines like nitrogen and sulfur, whereas H alpha, H beta, and oxygen 3 are fairly constant. And this is why our models move in that particular way on the PPT towards the linear Seyfert area. And we did that without assuming a super solar metallicity constraining that value. So this is it.
Thank you very much, Evgenia. You were not so fast as you promised.
Okay, sorry.
That's good.
Okay.
So questions? Elena?
Thank you. Very nice talk. I'm completely new to the topic, so excuse me if my questions are not very reasonable. I'd like to, if you go back to slide 33, and hereafter there are a few slides where you show the model grid for nitrogen and sulfur, and whether, while the models seem to agree with the nitrogen emission, they don't agree with the sulfur.
Yes.
So do you have an explanation for that?
Yeah, we expect that it might be due to the different region where this emission comes. So it might be that sulfur lies in different areas, maybe more in more distant areas from the source of the cosmic rays than nitrogen 2. But in general, nitrogen 2 is a bit more difficult to fit because in the growth models as well. Okay. Yeah, in the growth models, they also reproduce the nitrogen with the higher, the super solar case of metallicities, so forth. Whereas the sulfur was, is the same. Where is it? Whereas the sulfur was fitted with not that high metallicities. So in general, nitrogen seems to need a more drastic mechanism to be reproduced in general, so in other studies as well. They're going to the most extreme scenario such as we.
Okay, but you measure the emission lines from the exact same regions.
Yes.
And they should have the same physical properties.
Yes, but they could be deeper in the layers, so I don't
The
know.
models are an oversimplification.
That's
So
the
you-
other.
You put a single cloud and you simulate the response of the cloud. In reality, the medium is probably more stratified. Even if you are measuring the same aperture,
Okay, you have different.
maybe the sulfur to emission is not coming exactly from the same area. And you realize that when you measure, for example, not in this case, because we don't have the tracers, but when you compare temperatures for nitrogen and sulfur, they don't match. Sulfur has a lower ionization potential, and sulfur 2 can survive in neutral regions where the ionized gas is not. So I think those differences come from there because other works, other models, they also cannot fit everything with the same parameters.
I understand. Okay. Thank you.
Question on the same page. Thanks for the talk. How big are the error bars in the data points here?
How big?
Yeah.
I didn't get the
The error bars. How in the data points?
the error bars. I haven't done that. I don't know how big they are.
Because on a visual comparison,
If
you
it
can
could be.
take some messages from there, but error bars can play a.
Yeah.
I guess they are well
They're
constrained,
small.
right?
They should be of the order of
The size of
10,
the
20% at most. I think. So the idea was to show the dispersion in the excitation conditions that you have in different regions around the nucleus. So that is larger
than the other.
than the other.
Yeah, I'm not a person who is not working in this topic at all, but why your observational sample just contains only 15 galaxies?
Why do I fit only galaxies?
No, why do you have only 15 galaxies in your observational sample?
Because it was convenient to use their MUSE data, and because they had clear MUSE data with high signal-to-noise ratio. Also, it would be a lot of work to open the galactic sample, and NCC 253 kind of was an extra because of the cosmic ionization rate measurements. But yeah, in general, we focused on the apertures, not so much on using a lot of galaxies.
Are you planning to bring 100,000 more galaxies here?
No.
No?
You need a spatial resolution
Okay.
to
Well, I think
To buy
that would improve the things because in these three cases, you already cover more or less the areas where the slow data are. So the point is just to compare the area that are covered by the models with some real data. But if you take a SLOAN, you can see the whole distribution. No? If you plot the millions of galaxies from a SLOAN, you would see that they go more or less from here to there and to here. No? So the point was to focus on the models.
No, Luigi Spinelli.
Question?
Yeah, Luigi?
Yes, well, very nice presentation, Evgenia. I just have a comment. You have different results in cosmic ray power from one line to another line. How do you explain this? The cosmic ray flux is different in different regions of these galaxies, or these lines do have a different sensitivity to cosmic rays. I mean, this is the point. The other idea, I was talking with Juan, is to use also infrared tracers to see how the effect of cosmic ray is. So you are going to work in this direction also, right?
Yeah, we're going to do the infrared lines. This is the next step to find some diagnostic on the infrared lines as well. Yeah, it can be both because these lines, nitrogen 2 and sulfur 2, do not have also the same ionization potential. So they're probably, it's logical to me at least that they are differently affected by the cosmic rays. Also, the reasons we told before that they might be coming from different gas cloud layers, or they could as well, I don't know, behaving in general in a different way because we cannot reproduce to the full the environment they're coming from. So maybe the metallicities are a little bit different in each area, the composition of the gas. So these are all very nice to examine.
Okay. Thank you.
Okay. No? We thanks again the speaker. Okay. It's a Hannah's birthday.
Birthday.
Happy birthday.
Happy birthday!
You know this is being recorded, you know?
It's still live.
Stop it.
It's not,
Am I missing cake?
You're missing cake, Alejandro.
Oh no. Anyway, nice presentation. I was about to ask about the nebula, but
You can
Anyway.
ask.